Just start the recording over here. The goal of this lab, the objective of this lab is to create a Python file that you can import that is going to be a representation of a graph object, okay? We're looking to come up with some dictionary, some structure, some maybe class object that represents a graph object. That is the goal. The autograder is going to take your code and it's going to import it. So like in the way that we say import sys or import time, you're going to write a file and it's going to say import the name of your file as something or other. It's going to import your file. What it's going to do is it's going to try to run the functions that you'll see described on page 4. So page 4 has a bit of functions, and the purpose of these functions are to construct grabs of arbitrary natures. So we're looking to create grabs, and we're going to create a some sort of representation of this. The nomenclature is going to be a little bit tricky and weird, so you'll see things that look like this going on inside of here. My goal is to get through as many of these as possible today so that you can go home and read this and identify things that maybe make a little bit more sense, so it becomes more readable. Really, before we get too deep into this, though, I think it's important to talk about graphs, and that's why this also begins at the start by just talking about graphs. And so graphs are, there are lots of different things that we can do with graphs. You may have encountered these guys. We saw them before. We were talking about A-star, we first them a little bit. We have things like networks, supply chains, distribution networks, travel, railroads. You know, you can think of lots of different things that we would use graphs to represent. So the typical way of representing these guys is through circles and connected lines. Within these connected elements over here, these are going to be our vertices or nodes, right? So these are our vertices. Are you turned on? Okay, so it's not drawing. That's fine. Our vertices are the dots, and the edges or the links are the lines that connect in between them. So here are our lines that connect in between them. These are our links. You can think of these things as being, oh, that's nice. You can think of these as being ways to transition between states or something like that. So for example, if this were flight paths, you know, maybe we have some city A, maybe you have New York City, and then you have I don't know, Richmond, and then we have like Berryville. Maybe there's a local flight that you have to fly to Richmond in order to get the flight to Berryville. But then from there, you can go back to JFK and you can reach anywhere in the world. There are lots of different things that we would use to represent this. One of the parameters that you also see within graphs is the notion of size. The size of the graph is the number of nodes that we have inside of here. So here I have 1, 2, 3 by 1, 2, 3, 4, 5, 6. I have 18 nodes, so this graph has a size of 18. Let's see other things. Our original graph from here before, this graph has a size of 7 because it has 7 nodes. There's also going to be some terminology that you see on these first pages, like undirected graphs and directed graphs. An undirected graph means that there isn't necessarily some sort of implied direction between these two nodes. You can take the plane from Berryville to Richmond. There's no, it's the road, you can take that road, whatever. You need to go through here to get there or wherever. We're going to have these grid world graphs. In this case, we have this quad nature. We're going to be working primarily with grid world graphs in this lab. These guys all have undirected connections in between them. Our goal in this And the goal with all the sort of scary nomenclature and the things that you see people talking about perhaps is to define some specification that is going to allow us to selectively remove and add nodes. Our goal in this lab, all this is doing is to create some graph where we can specify a size and specify the connections that exist within them. So here you'll notice that there are some connections that don't necessarily exist in that native state. So we're going to be looking to trim and prune these graphs through commands. So to create, to trim, to prune, and to do things like apply rewards. So if you think of, I don't know, games, Othello, this is going to be kind of scaffolding you up for Othello, getting you ready for Othello. But even in other things like Minesweeper, you can think of there being some reward, positive or negative or different, or chess. You get different rewards as you go between different places within this board. Yes.
So it's like old weights.
Weights, you can effectively think of, yes, or weights. So when we have this construct that we're going to make here, this will serve that basis to do things like Othello, which is going to be getting soon, which is going to be the entire AI Othello tournament, right? And so we need to have a system that gets us ready, thinking, structured, prepared to go in that direction. That's kind of where this is going. The undirected graphs are represented by this beam, right, that has no arrow associated with it. However, directed graphs do have an arrow within them. So in the directed graphs, this perhaps is implying, I don't know, maybe some supply chain or something like that, right? Like maybe this is the foundry over here, and he sends the iron to this guy, and then he's happy with his iron, and that goes to this one who makes the camshaft, and then this guy has the other things, and they send the camshaft, and it all goes into this, I don't know, whatever. Like there are states, there are flows, there's some representation of a thing that's happening in this graph. A ski slope, right? I can go up this lift and I can go down to this lodge and I can go down to this lodge, but from this lodge, I cannot go back up the slope to get to this top of the lift. Not possible. Within here, let me just remove my dots. There's also some nomenclature that you're going to find on this first page. First and second page, things like the size. So we already briefly talked about the size of the graph. The directions associated with the graph, you're going to see the terminology in here called digraph. So if it's a directed graph, that is what the digraph. I think at the base of page 4 or 5 or something like that, it says something like all graphs in this lab are digraphs. That means that the base presumption from these graphs in this lab is that you're going to have directed arrows. There's also a base presumption that the default state, and we can talk about the default state. The default state is presumed to have arrows kind of bidirectional. And unless you explicitly specify it, you don't have nodes that have routes and paths to themselves. Those can be explicitly specified by this nomenclature described in this packet, but they're not inherently part of it, and you would have to explicitly construct them. There's some graph terminology like paths. The path does not repeat nodes as you transfer along links and edges from one to the next and the next. So in a path, here I have a path of length 0. Here's a path from this graph, this node to this node. Here's a path. Here's a path. You don't visit the same node within a path. In a walk, you return to the node where you started. So that's just a graph terminology thing. Walks, you return to where you start. Path, you don't. We're not heavily focused on that right now. Let's talk for a moment about what this is looking for then, and do subgraphs, Cartesian products. I'll leave it to you guys to read through that, but let's talk about what we're going for right now with this. So I'm going to jump around a little bit. If you guys look at page 14, I'm going to jump to page 14. So you can kind of see the way that this thing is going to be working. So on page 14, you're going to see that in this lab, your file is going to be tested in a very different way than your other files were tested. Previously, what happened was you had a file and it was just run, it either ran on some other collection of test cases, or it was spammed with test cases. One way or the other, things were happening. Now something different is going to be happening. Now your file is going to be imported like path or like sys. It's going to be imported. And the methods that it imported are going to be invoked from it. So we're going to import your file. Have you guys used Python files? Have you created like other files for yourself in the past where you import your own file and use your libraries before? I have some nods and some no. This is surprisingly straightforward. I can give you a quick show on this. So, for example, here I have this file. I'm going to just open this. This is INP01 or IMP. I have imp or import 01 and 02. If I navigate over to this thing, so here we go. I'm not going to call Python to demonstrate this. I'm going to use the console. So I'm throwing another concept at you right now. Are you familiar with the Python console? This is kind of like a Colab, but different. What we do is we type Python directly at the terminal. And you're going to notice that this looks very different, right? I have my 3 arrows over here. I'm now at a Python terminal. In the Python terminal, things that I tried to call in the past don't work there. I can't type CD, right? CD is not defined. That doesn't make sense. I can't type ls or dir or Python, whatever. These things don't exist the same way because I'm now in a Python environment. And in this Python environment, I can type things like import sys. And I get the sys library. Whereas, and you can exit with exit open close. Whereas if I say import sys just at the terminal, like in your Mac or in here, import is not recognized. So I'm moving the terminal into an interactive Python environment, okay? So in order to test this, you can, sorry, I'm going to go into my Python and I'm going to import IMP02, for example. I can import my file. I can import this guy as Josh. And within here, I have, for example, Josh.1. That returns a 3. I'm running this file from the library. Yes, in agreement. I don't want to dumb this down too much, but I think it's also important here. I could say Josh.do something, right? Josh.do something. It adds them together. It's a fascinating thing. So your code is expected to do this. Just to be clear, I'm going to go back over here to page 4 just for a second. Your file is going to implement these functions that you see on page 4. These 8 functions, I think I said 11, but you're going to implement these functions and your code is going to do the right thing basically with these guys, okay? And the right thing is to create a representation of a graph as is defined by these things. Tearing right along. what this thing is going to look like, if we look over here, and you can begin to see this, it doesn't really matter what we imported as. Here, he imported the name of the file as PG. And then he ran the functions pg.parse on the directives, pg.graphclass. He could have called it as blah, as foo, as Josh, as whatever. And then they interactively ran these functions. So what is it that this thing is supposed to be doing, right? Like, what is it that we're actually doing here? Let's move our story along. I know I'm jumping around a little bit over here, but I'm going to go to page, actually, I'm going to go to page 14. So you're going to see a lot of different things that explain the first line that the first line that's going to be called is this graph parse. You can see right here, pg.graph parse. Graph parse takes in the input specifications and it constructs this graph object. It takes in the input specs and it parses the graph object, okay? And it's going to create some arbitrary structure. Maybe it has nodes, maybe it has 4 nodes, and then it has some arrows going in between them. It knows how to understand all of these other codes, which are surprisingly less complicated than they look like once we get used to them. It's going to take all these codes and create a graph. We're going to start by talking about the G specification inside of here to get a sense of what this G specification looks like. But the idea is that we parse the input specs and that we're going to create this graph object out of it. And that graph object, he's going to be some graph class object. This is going to be some dictionary or whatever that represents this graph. And that object can be passed to the other methods. Notice that he's being passed to other things. So I create my graph, and then I run methods on this graph that I've created to get various elements out of it. The first specification we're going to work with, the first thing to make sense out of this is this grid world specification, which basically specifies the number of nodes on this thing. So for example, when I say a G12, and we'll pick up over here on page 5, I know that the order is a little bit out of what I'm thinking here, but we pick up on page 4 and 5. The first directive is this graph directive. So this is kind of defining, right? So this is giving an example. The first directive that your graph parse could be passed is this G type directive. And G is a way of specifying a graph, a digraph is by our presumption over here. And there isn't really a lot of description of this, of what this exactly looks like. But what you would see, let me just jump around over here. What you'll get is some sort of spec like this: GGR5, R2, GN4, GN5, blah, 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 G12, blah, blah, blah. One of the first things you're always getting passed through is this G specification. This is a specification that you're in a grid world, a G-type graph. And if I get something that says G9, what it means is start working with something like this. G9 says start with a digraph of size 9. Okay? G9, start with a digraph size 9. There's a statement inside of here. I believe it's on page 6. And it says something like, for G-type graphs, the width of the graph defaults to the smallest int, at least the square root of the size of the graph that evenly divides the graph. So what this is saying is that the width of this graph, this grid world, this G graph, the width is going to be at a minimum the square root of 9, which is 3. If 3 evenly divides the size of this graph, it has a width of 3. 3 does. This graph has a width of 3. For a G12 graph, the square root of 12 is what? Like 3.3, 3.4, 3.2, something like that. 3.4-ish. So we start working at 4. Does 4 evenly divide 12? Because we can't go less than 3.4-ish. So we start working at 4. So we start working at 4. Does 4 divide 12? The graph has a width of 4. So they go wide before they go tall. They go wide and then they go high. Wide, high, wide. You can specify the width. So you can say G12W3. I don't suggest that where you worry about parsing width at first, but you'll see in some of the examples later on inside of here, G12W3, G12W6, or something like that, you can explicitly specify the width of a graph. In this case, I have a width of 3, so that overrides the default. If I were to say, for example, G12W2, I would get this width of 2 graph, right? And it would go all the way down for 6 of these guys. The math of this is not that complicated and is well within the reach of what you guys will be doing and finish tomorrow. You can do that. I'm positive. Okay. That's math. You can write a function that takes the square root of an input number. For a G10, the square root of 10 is what? 3.1, 3.2-ish. So we start with a 4. Does a 4 evenly divide 10? No. Does 5? Yes. So we just have this loop. The width of 5 is inferred off of this. It's also possible, and as you read through this, and I'm going to encourage you to read through this, for these n-type graphs. N-type graphs are not presumed to be grid world type graphs. So if I have a GN7 over here, or a GN10, this has 10 nodes. It's a none-type graph. There's no implied rectangular structure to this graph. Thank you. Right? So the W of 0 is inferred. N is 6, an n-type graph of n6. So all of a sudden, my hope is that you guys can look at some of these examples, and there's a little bit of a directive that's less scary. This made a G12 graph, right? That started with a graph of a grid world of size 12. The first step in this directive was to create this graph that this is going to have a 4x3, and it's going to have bidirectional edges between all of these guys. That's what this thing is doing right here. The point of the rest of these is to trim and to prune down all those connections, those bidirectional connections, to make something interesting. Let's take a look at other things inside of here. So there's a lot of, here we go. Like you could also see, for example, something like this. Here we go. Look at this guy. G6, right? A G6 that created a grid world type graph. Width is 3. Height is 2. If I had a G11, what do you think the width of a G11 graph is? 11. There you go. Cooking with gas. Why is the width of a G11 graph 11? Yeah, it's prime. Thank you. I know you know the math, but like it's a matter of wrapping your brain around the problem in front of us. Okay, tearing right along. If you specify a width of 0, a G graph becomes an N graph. Sure, you can work with that. And by default, this thing gets a W of 4. Yes. So if I say G6 W0, this is that. This is a G6 W0. Okay. Good question. So the next thing, now on page 6, and I want to just have a little bit of a talk about the scariness of identifying this VLCS business. Oh my gosh. So let's assume we have a graph of size 12. The point of these vertices specifications is that we're going to be wanting to add and prune and remove vertices that go from edges that go from one vertex to another. But you may want to do many at the same time, right? I may want to remove like 6 or 8 of these guys at the same time, or 6 or 8 of the nodes at the I may want to do some bulk operation and select much in the same way that we select multiple indices from a list. So the idea here is that when you're indexing vertices, you can use something like a list notation. These guys are going to be identified as 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So they start 0 enumeration over here. So if I were to say vertex -3, vertex -3 becomes -1, -2. That was the 9th one, right? Which is basically saying vertex of -3, that's spot 9 within here. Vertex of 1, step 2, that's 1, 3, 5, 7, 9, 11. Vertex of 1, step 2 is from 1 to 11, stepping 2. We stop at 11 because this is assuming that graph of 12 over here. From -2 to -3, comma, 3 to 4, backward stepping like in lists. Positive stepping, notice that this is the step interval, and you have your first -1, -2, -3. That's a collection of 3 things. The only weird thing is the hashtag notation. The hashtag notation presumes a square that begins and ends at the indices specified. So for example, if I have 4#7, that takes 4, 5, 6, and 7 right here. So 4#7, sorry, 4#7 gives me 4, 5, 6, and 7. And then the other one is 2:4. That was 2, 6, and 10. So 4#7, let's go here. 4#7 was 4, 5, 6, 7. And the other one is going to be 2 going up by steps of 4. That was 2, 6, 10. So my total indices were 2, 4, 5, 6, 7, 10. So if you get a spec for 4#7, 2:4, that meant 4, 5, 6, 7, 2, 6, 10. That set of these guys. 4#7, 2, 6, 10. And it groups all of these together basically as a list. It basically is saying all of these vertices. The command that you might be interested in is perhaps remove all connected edges from there, right? So we might have something where you say, like, you might grab them because you might want to say, hey, toggle all of the connected nodes over here. You might want to say, like, turn this off, turn that off, turn that off, turn this off, turn that off, turn that off, turn that off, turn that, boom, boom, That's why you would grab all these things to do a bulk operation. All right.
So. Top left corner, bottom right.
Top left, bottom right. That's the hash syntax. Okay. So, yes, this is confusing to look at, but it also might not be that bad. So like V2B, like there's some other examples later on that kind of get into this. You would start seeing something like that over here. So for example, here, everything up to the second last, basically. The vertex of everything up, or sorry, 0, 1, and 2. 0, 1, and 2. This gets vertices 0, 1, and 2, and it applies the B to them. So this made a graph of type 6. It grabbed the vertices 0, 1, and 2, and it applied the B operation to them. Okay. So that's the kind of stuff that this thing is looking to do. The nomenclature is a little bit weird, but that slicing operation is a way of identifying multiple vertices when we do something like toggle all the connections to them. Question.
So B is a function that you apply on the 0, 1, and 2.
That's exactly it. B is a function that you would apply in 0, 1, and 2. So much in the same way that we don't know what we didn't know what this is, and we'll get there. Like we can talk about, and I would leave it to you guys to read through this and identify what the B is. It means just remove everything. It means toggle everything that was there. So basically blast anything that's connected, bring in new connections where there weren't things connected. Tearing right along. Possibly the weirdest thing to work with over here. And I don't know how much time I actually have for this. Do I have like 5 minutes? Something that I think is worth for you guys you can figure out other things within here, okay? I'm gonna scroll back a little bit over here. I would argue that you can, and I'll try to make some videos that are helpful for you here. I would argue that you can go in and read and say, oh, this is toggling the edge between, this toggles the edge between 1 and 2, the directional edge from 1 to 2. This toggles all edges between 1 and 2. This is only one directed. This is everything. This is a directed edge. This applies a reward. This applies a reward. We can work with that. The weirdest thing you will encounter, in my opinion, is this stuff. What the heck is this stuff? Okay. This is a compact notation of what the graph looks like. This is a compact notation of the graph. So I'm going to give you a moment over here, and I know you want to leave and go eat lunch over here, but let's do this. So a G6, I would argue that a G6, that this is the compact notation for a G6 graph. You'll notice that there are 6 elements inside of here. Each of these guys, each symbol refers to the connected edges. It's a description. It's a compact notation for the connected edges at that vertex. Okay, it's a compact notation for the connected edges, directional edges at that vertex. So let's take a moment to step through. Let's say we have a G6 over here. Remember that width of 3 is inferred. There's a spec that says R, and you can play along with me. You can read this on page, you guys want to flip to page 10? If you flip to page 10, and you look at the table that's right here, you'll see RSE. Do you see RSE on page 10? Okay, I'm looking at this table if you see nothing else. R in the compact notation. Wow, is that text? Interesting. R means I have directed edges to the east and to the south. For his adjacent neighbor, notice again that we have 6 symbols, right? B is the compact notation that says I have an east, a south, and a west. So if you look at this graph on page 10, if you look at the chart on page 10 and find the V, you'll see that V means that there are edges to the west, the south, and the east. Knowing that, what do you think the letter is going to be over here on the right on this one? What's his or her, what's their letter going to be? They're going to be a 7. Absolutely. Okay. So this is a 7 because that 7 has an edge to the west and it has an edge to the south. Okay, what's this guy going to be? My lower corner over here from the chart on page 10. Say it again. Yeah, he's an L. I jumped ahead. L up J. So we have a compact notation that represents the graph. So I would argue that with this in mind, we can now look at these examples on page 9 and begin to infer what this is doing. A G6 made this compact notation over here. Graphs have a default reward of 12, because that's the default reward in this lab. We can talk about that. It had a width of 3. And this compact notation was inferred out of here. So what we're looking for you guys to do is really just come up with parse these arguments and figure out who's connected to whom. Once you get the language, it's actually not that scary. We'll talk through more of these cases tomorrow. However, and so for here, for a 7, right? What is a 7? What is a 7? South and west. So you can see, we can look at this 7, and this killed the edge. This killed the connection. Sorry to use term. He killed the E1, 2. That killed the directed edge between 1 and 2. It removed it. So it changed it from a V to a 7. Okay. So the idea is that you're going to create a graph, toggle edges for each specification, and then you'll be able to say, well, you'll get some prompt. It's like, how many edges are connected to 6? And you'll be like, oh, that's 3, because you parse the arguments. It's not that scary if we go through this systematically. I'll give you more test cases tomorrow. I would highly, highly, highly encourage you to at least read through this thing to get a sense of what this is doing. I will try to make some descriptive videos that go through these processes as well. Thank you for your attention today, guys. Give me once, yes. I just want to stop the recording here.